So if you just go ahead and pour yourself a glass of water, I mean, it seems like the simplest thing in the world,
Oh
right?
yeah, completely mundane.
Yeah, but if you actually look closer, there is this invisible microscopic tug of war happening right inside that glass. So today on the deep dive, we are totally decoding the hidden rules of fluids.
Right, because fluids govern pretty much everything around us.
Exactly. We're
Yeah.
taking you on a journey that starts with these tiny, almost, imperceptible interactions between individual molecules, and then we're scaling that all the way up to the massive crushing pressures inside, like industrial pipelines.
It's a huge leap, but it all connects.
It does. And our mission today is to give you a custom-tailored shortcut to being fully informed on this. We want to make sure you get all the big aha moments without getting, bogged down in massive textbook information overload.
Because the textbooks on this are, well, they're dense.
Very dense. So, okay, let's unpack this. Because while liquids and gases might seem straightforward, they are actually hiding some absolutely wild secrets that govern the physical world around us.
They really are. I mean, the physical rules governing fluids dictate everything from how a tiny plant gets water to how a massive oil refinery operates. But to really grasp those secrets, we kind of have to establish a baseline first.
Right. What are we actually talking about when we say fluid?
Well, basically, a fluid is essentially any substance that flows and, assumes the shape of its container. So that means we aren't just talking about liquids like water or oil.
We're talking about gases too, right?
Exactly. Gases like steam or even just the air we breathe are fluids.
Yeah.
And if you really want to understand how a massive container of fluid behaves, you can't start at the macro level. You have to look at the tiny building blocks of matter first.
Okay, so we need to zoom way, way in, like down to the atomic level.
Right down to the atoms.
So before we talk about massive tanks and pipes, let's look at what actually makes up a fluid. I mean, matter is broken down into pure substances, right?
Exactly that. At the most fundamental level, we have elements. And those consist of just one single type of atom. So, oxygen is an element, hydrogen is an element.
Okay.
But when you combine two or more different elements, you get a compound.
Like water.
Right, water is the classic example. It's a compound made of two hydrogen atoms and one oxygen atom, H2O. And what's interesting is that you can actually reverse that process physically.
Wait, really? You can just unmake water?
Yeah. If you run a direct electric current through a pool of water, you can literally split that water compound back apart into pure hydrogen and pure oxygen gases.
Oh, wow. So when these molecules are just like hanging out together in a glass, they aren't just floating around randomly. They're constantly interacting. Right?
Oh, they are locked in a constant microscopic battle. It's all about intermolecular forces. And the two main forces at play here are cohesion and adhesion.
Cohesion and adhesion. Okay.
Yeah, so cohesion is the attraction between the same type of molecules. Water, for instance, is highly cohesive. It loves other water molecules.
Why is that? Is it a magnetic thing?
Basically, yes. It happens because water molecules are polar. There's this unequal sharing of electrons within the molecule itself, which gives the oxygen side a slight negative charge and the hydrogen side a slight positive charge.
It's like a literal magnet.
Exactly like tiny magnets. The positive side of one water molecule is fiercely attracted to the negative side of another.
Okay, I like to think of cohesion as a tight-knit family that always sticks together.
That's a great way to look at it.
And then on the flip side, you have adhesion, which is the attraction between different types of molecules. So as cohesion is the tight-knit family, adhesion is kind of like making fast friends with strangers.
Right.
It's the water molecules deciding they really like the molecules of, say, a glass window.
And you can actually watch that battle between the family and the strangers play out with your bare eyes.
Really? How?
Well, if you pour water into a glass U-tube manometer.
Which is like a U-shaped instrument for measuring pressure, right?
Yes, exactly. A simple U-shaped glass tube. If you put water in there, adhesion actually wins the tug of war. The water's attraction to the strangers, the glass, is actually stronger than its attraction to its own family.
So what does that look like?
The water literally creeps up the inside walls of the glass. It creates this scooped-out concave surface at the top of the liquid line. We call that a meniscus.
Oh, right. Because it's actively trying to maximize its physical contact with the glass.
Exactly. But we see this with water. Mercury behaves completely differently.
Yeah, mercury is totally weird.
It is. If you put liquid mercury into that exact same glass tube, Its cohesive forces, its internal family bonds are incredibly strong, so it actively repels the glass.
So it does the exact opposite of water.
Right. Instead of creeping up the sides, it tries to minimize contact. It pulls away from the walls and creates this convex meniscus that bulges upward in the dead center of the tube.
It's like it's trying to hide from the glass. That molecular attraction is strong enough to defy gravity.
It really is.
And, this isn't just trivia. People who work in trades, like plumbers, they rely entirely on these invisible forces when they're soldering or brazing pipes together, don't they?
It is the entire foundation of those trades. When a plumber joins a copper pipe to a fitting, they actually leave a microscopic space between the two pieces of metal.
The capillary gap, right?
Yes, the capillary gap. They apply a chemical flux paste to the metal to encourage adhesion. Then, when they heat the joint and melt the liquid metal solder, the forces of adhesion and cohesion work together
To do what?
to physically pull that heavy liquid metal upward. It crawled right up into the gap against the force of gravity, completely sealing the joint.
That is wild. I mean, if these forces are that powerful, it makes me wonder, what if you had a fluid where the cohesion exactly matched the adhesion, like a perfect tie in the tug of war? What would a droplet of that fluid look like resting on a table?
Oh, what's fascinating here is that if those two forces find a perfect equilibrium, the droplet forms a mathematically perfect dome.
Really? A perfect dome.
Yeah, it reaches this precise balance between wanting to spread out flat to, maximize contact with the table and wanting to beat up into a tight spherical ball to maximize contact with itself.
That's amazing.
And observing these forces helps us understand everyday phenomena too, like capillary action. When water creeps up a remarkably narrow glass tube, it will keep climbing and climbing to touch the glass.
Until what? It can't go on forever.
Right, until the sheer physical weight of the water column becomes too heavy for the adhesive forces to pull, and it just stops.
So eventually, the physical weight of the fluid pulls it back down. And that weight, how densely all those tiny molecules are packed together, that changes entirely depending on whether we're looking at a gas, a liquid, or a solid.
Exactly.
So let's get into density.
Density is crucial because the physical state of the matter dictates how the molecules interact. Let's look at water across its three states.
Okay, starting with gas.
Right. If you have water vapor at gas, those molecules are widely spaced out. They're bouncing all around a room. And because there's so much empty space between them, gases are highly compressible. You can squeeze them into a smaller tank.
But if you look at liquid water,
The molecules are densely packed together. They can still slide past one another and move freely, which is why liquids flow. But because they are already so close, liquids are only very slightly compressible.
and then in solid ice, those molecules are locked into an elastic, rigid grid. They basically can't move past each other at all, making solids essentially incompressible.
Right.
So density is really just a measurement of how much mass is stuffed into a specific volume of space. It's mass divided by volume, usually measured in kilograms per cubic meter.
Yes. Though when industrial engineers are dealing with gases, like in steam power plants, they often flip that math entirely.
Flip it how?
They use something called specific volume, which is volume divided by mass.
Okay, so why do they do that?
Well, instead of asking how much a cubic meter of steam weighs, they ask how many cubic meters of space does 1 single kilogram of this steam take up? It's a much more practical way to calculate when your fluid tends to just expand to fill an entire room.
Ah, that makes sense. And when we want to compare different fluids quickly, we use relative density or specific gravity.
Right.
And that's basically just taking a fluid's density and comparing it directly to the density of pure water. It's just the quickest way to know if a mysterious fluid is going to sink or float when you mix it with water.
Exactly. Water is the universal benchmark.
Okay, wait, hold on a second. I have to push back here.
Oh.
You're talking about pure water as a benchmark
Ah.
and using exact calculations, but I was definitely taught in high school physics that water's density is just a nice, even 1,000 kilograms per cubic meter. Were my teachers just, lying to me to save us the headache?
Well, I mean, not exactly lying. They are giving you a perfectly acceptable baseline for high school physics. If you are doing general calculations where extreme accuracy just isn't critical, 1,000 kilograms per cubic meter works perfectly fine.
But it's not the exact truth.
No. The physical reality is that density is not static. Thermal expansion changes it. When matter heats up, the molecules gain energy and they push further apart from each other.
So the fluid physically takes up more space as it gets warmer?
Right. At 4 degrees Celsius, water's density is incredibly close to that high school number. It's actually 999.97 kilograms per cubic meter,
Okay, so pretty much 1,000.
basically. But if you heat that exact same water up to 15 degrees Celsius, the molecules spread out. The same exact mass of water now takes up a larger volume, so its density drops to 999.10 kilograms per cubic meter.
Okay, I can see how that's mathematically true, but why does that tiny fraction of a decimal matter to anyone outside of a laboratory?
Because in industrial instrumentation, precision is literally everything. I mean, imagine you are managing a massive chemical plant or an oil refinery.
Okay.
You are measuring millions of gallons of fluid flowing through pipes every single hour. If you assume the density is 1,000, but it's actually 99.10 because it's a warm day out, that tiny fractional error gets multiplied millions of times over.
Oh, wow.
Yeah. Suddenly, you've miscalculated your inventory by thousands of gallons. You can't just guess the density. You must know the exact temperature of the fluid at all times.
That really puts it in perspective. Okay, so now we know fluids have these incredibly specific temperature-dependent densities. Let's look at what happens when gravity gets involved.
Right.
Because gravity pulls down on all that densely packed mass, and that creates pressure.
Specifically, static pressure or hydrostatic pressure.
Right.
And because liquids are fluid and they take the shape of their container, this pressure doesn't just push straight down on the floor of the tank.
It pushes everywhere.
Exactly. It is an area-distributed force. It acts perpendicular or normal to any surface submerged in it.
Like a submarine.
Yes. If you drop a submarine into the ocean, the water pressure isn't just pushing down on the roof, it is constantly trying to crush the submarine inward from the sides and the bottom too.
That's terrifying, actually. But calculating that crushing force is actually pretty straightforward, right? The pressure at any given depth equals the fluid's density times the gravitational constant times how deep you go.
That's the formula, yes.
But there is a concept here from the sources that really twists your brain about how pressure behaves inside a confined space, and that's Pascal's law.
Oh, Pascal's law is a total cornerstone of fluid dynamics. It basically states that if you apply external pressure to a confined fluid, that pressure increases everywhere inside the fluid perfectly equally.
Okay, let's walk through this so I can visualize it properly.
Yeah.
Imagine you were standing next to a massive open-top water tank. It's, say, 15 meters deep. If you want to know the absolute pressure at the very bottom of that tank, you can't just calculate the weight of the water itself. That's just the gauge pressure.
Exactly. You have to account for the atmosphere as well.
Right.
We basically live at the bottom of an ocean of air, and that air has real weight. Standard sea level atmospheric pressure is roughly 101 kilopascals. That is a massive, invisible physical weight bearing down on the surface of the water in that open tank.
So what does this all mean for someone actually trying to measure this stuff?
Yeah.
Like if I install a mechanical pressure gauge at the bottom of that 15-meter tank, the needle might point to 147 kilopascals.
Yeah.
It's just measuring the water.
Right. The gauge pressure.
But the absolute pressure, the true physical crushing force that the metal walls at the bottom of the tank are experiencing is actually around 248 kilopascals because we have to add the invisible ocean of air sitting on top of the tank.
That is the exact distinction between gauge pressure and absolute pressure. The gauge ignores the atmosphere because it's calibrated to 0 in the open air, but the tank itself still physically feels it.
Okay.
Now, if we connect this to the bigger picture, let's look at Pascal's law in action. Imagine we weld a heavy steel roof onto that exact same open tank, sealing it shut completely.
And now it's a closed system.
Right. And there's a pocket of air trapped between the water and the new roof. If we pump more air into that space, pressurizing it to, say, an extra 8 kilopascals,
Okay.
Pascal's law tells us that those 8 kilopascals don't just push on the surface of the water. That force transfers equally through the entire 15-meter depth of the liquid. Every single drop of water, all the way down to the welded floor, instantly feels that exact same 8 kilopascal increase in pressure.
So the fluid is just a perfect messenger for the force.
Precisely.
And this brings us to the flip side of pressure. Because pressure increases the deeper you go, the pressure pushing up on the bottom of a submerged object is actually stronger than the pressure pushing down on the top of it. And that mathematical mismatch gives us buoyancy.
Archimedes' principle. It states that the upward buoyant force exerted on an object is exactly equal to the weight of the fluid that the object physically displaces.
Okay, let's put some real numbers to that. Say you drop a solid 1 cubic meter block into a pool.
Okay.
It physically pushes exactly 1 cubic meter of water out of the way. And we know from earlier that a cubic meter of water weighs roughly 1,000 kilograms.
You're right.
So because it displaced 1,000 kilograms of water, the pool pushes back up on the block with exactly 1,000 kilograms of force.
Exactly. And the outcome depends on the block itself. If your block weighs 1,200 kilograms, gravity wins. It sinks to the bottom.
Makes sense.
But if your block only weighs 500 kilograms, the upward force of the water is actually so strong that the block floats. And it floats with exactly half of its volume sticking out into the air.
Wow.
And let's take that a step further. What happens to the heavy block that sinks?
The 1,200 kilogram one.
Right. It experiences a phenomenon called apparent weight. Because the water is constantly pushing up on it with 1,000 kilograms of force, that 1,200 kilogram block will actually feel significantly lighter when it's underwater.
Oh, I see.
Yeah, if you tried to lift it off the bottom of the pool, its apparent weight would only be the equivalent of 200 kilograms.
Okay, here's where it gets really interesting because this isn't just a fun observation. It's a legitimate tool. I mean, it's exactly like stepping into a swimming pool and suddenly feeling light enough to do handstands.
Exactly.
You haven't lost any actual body mass. The pool is just lifting you. And industrial engineers use this exact concept to measure fluid levels inside sealed tanks using these devices called displacers.
Displacers are a brilliant application of apparent weight.
How do they work?
Well, instead of using a bobbing float that rides the surface of the liquid, which, can get stuck or bounce around or break, they use a heavy, solid stainless steel cylinder. It is suspended from a highly sensitive force sensor at the very top of the tank. And because it is solid steel, it's far denser than the liquid, so it will never float.
It basically just hangs there.
Right.
But as the tank slowly fills up with liquid, the liquid swallows up the metal cylinder. And as it gets submerged, it displaces water, so its apparent weight drops. The sensor at the top of the tank is basically just weighing how much the rising fluid is lifting the heavy metal cylinder.
Exactly. And the beauty of it is that the cylinder doesn't have to physically move at all. It remains perfectly still.
That's so smart.
It is. As the liquid level rises and falls around it, the changing buoyant force does all the complex mathematical work. The sensor simply reads the changing weight of the cylinder and instantly translates that into the exact depth of the fluid.
That's incredible. But, up until now, we have only been talking about static fluids. Fluids just sitting perfectly still in a glass or a tank or a pool.
Right, static states.
The real complexity, and I guess the real power, happens when we open a valve and let all that stored pressure energy turn into actual movement. So let's talk about flow.
Moving fluids introduce entirely new dynamics. And the first thing to understand is that not all flow is identical. Engineers categorize flow into two main types: laminar and turbulent.
Laminar and turbulent.
Right. So laminar flow happens at slower speeds, specifically when a metric called the Reynolds number is below 2,000. In laminar flow, the molecules are highly organized. They move in straight, orderly lines, perfectly parallel to the walls of the pipe.
But they don't all move at the exact same speed, do they? I mean, because of friction.
Exactly. Friction plays a huge part.
Because the fluid right at the outer edge rubs against the inside walls of the pipe so it drags and slows down. Meanwhile, the fluid in the dead center of the pipe faces no wall friction, so it just rushes ahead.
Yep.
If you could somehow freeze the pipe and look at the velocity profile of the liquid, it looks like a stretched out, rounded bullet shape.
A parabolic profile, yes. But if you open the valve further, increase the fluid speed, and push that Reynolds number above 4,000, you fundamentally change the nature of the flow. You enter turbulent flow.
So it's not neat and orderly anymore.
Not at all. The orderly, straight lines completely break down. The fluid becomes chaotic. It's full of churning eddies and violent swirls, constantly mixing across the entire diameter of the pipe as it travels forward.
And because it's churning and mixing so thoroughly, the speed of the fluid actually averages out, right?
Yeah.
It creates a flat, uniform, blunt-nose velocity profile instead of that bullet shape.
Exactly. Now, when you have this fluid moving through a complex system of pipes, you also have to follow the continuity equation.
Which is what?
This is the rule that says mass flow rate must remain constant. Basically, what goes into a pipe must come out.
Flow continuity means you can't, magically lose or create fluid within a closed system.
Right.
So if you have a liquid flowing through a wide 34-centimeter pipe at a gentle walking speed of, say, 1 meter per second, and then the pipe suddenly hits a bottleneck, narrowing down to just 20 centimeters.
Okay.
The fluid doesn't just bunch up like traffic on a highway, right? To get the exact same volume of liquid through that smaller hole in the exact same amount of time, it literally has to accelerate.
It does.
In fact, it speeds up to almost 3 meters per second just to make it through the bottleneck.
It is forced to accelerate to maintain the constant mass flow rate.
Okay, applying this to industrial instrumentation, there's something totally counterintuitive in the sources about all this.
What's that?
Well, you would naturally think that engineers want nice, smooth, orderly laminar flow for their highly sensitive measuring instruments. I mean, the bullet shape seems so predictable.
Yeah.
But most advanced flowmeters actually need chaotic, churning, fully developed turbulent flow to work properly. Why is that?
This raises an important question about the difference between theoretical physics and real-world measurement. Think back to those velocity profiles we just visualized. In smooth, laminar flow, you have that bullet shape. The center of the fluid is rushing by incredibly fast, and the edges are barely creeping along.
Right.
If a flow meter is installed on the side of that pipe, trying to calculate the average speed of the fluid, a bullet shape is an absolute nightmare. The speed it detects will vary drastically depending on exactly how deep its sensors penetrate into the pipe, because the speed is so different at the edge versus the center. But in turbulent flow, the chaotic mixing forces the entire width of the fluid to basically move together.
Yes.
It creates that blunt nose profile where the fluid at the edge is moving at almost the exact same speed as the fluid in the center.
And that uniform blunt nose profile gives the instrument a much more consistent, reliable reading across the entire cross-section of the pipe.
Right.
Sometimes deliberately introducing a little chaos is exactly what you need to achieve perfect precision. That is so cool. So to wrap our heads around how all these moving variables interact, the changing speeds, the narrowing pipe diameters, the shifting elevations, the pressure, we have to look at the ultimate fluid cheat code, which is Bernoulli's equation.
Oh, Bernoulli's equation is, at its core, a profound statement about the conservation of energy.
Break it down for us.
It tells us that for an incompressible fluid flowing steadily through a pipe, the total energy at any given point is the sum of three distinct things: the pressure energy, the kinetic energy, which is its speed, and the gravitational potential energy, which is its height.
Okay.
Assuming there is no friction, that total energy must remain perfectly constant no matter how much the pipeline twists, rises, drops, or shrinks.
And one of the most fascinating concepts here is how pressure fits in. Because pressure isn't just a crushing force. It is actually a type of potential energy.
Yes, it is.
It is quite literally the physical work done by a mechanical pump permanently stored inside the fluid itself, ready to do work later down the line.
Let's play out how that energy shifts in real time. If your fluid is flowing along and it suddenly reaches a steep hill, it has to climb. It gains gravitational potential energy.
Right.
If, at the exact same time, the pipeline narrows, the continuity equation dictates that the fluid must speed up, meaning it also gains kinetic energy.
So it's gaining height and speed. I like to visualize the total energy of this system as a pie chart. And the most important rule is that the overall size of the pie absolutely cannot change.
Not without adding energy from outside, no.
Right. So if the fluid suddenly needs a bigger slice of pie for height, and it needs a bigger slice of pie for speed, that energy has to come from somewhere. The only slice left to sacrifice is the pressure.
Exactly.
So the pressure slice gets squished, the fluid's pressure physically drops to keep the total energy perfectly balanced.
That is a highly effective way to visualize Bernoulli's principle. If speed goes up and height goes up, pressure simply must go down to compensate. However,
there's always a however.
There is. Bernoulli's equation represents a perfect theoretical ideal. In the massive, complex pipelines of the real world, there is a hidden fourth slice of that pie, and that's frictional heat loss.
Ah, the drag on the pipe walls.
Yes. Fluid constantly rubbing against miles and miles of internal steel piping robs the system of energy, and it dissipates it as heat. Designing a system to fight that constant resistance to flow while making sure there is enough pressure energy left at the very end of the line to actually push the fluid into a storage tank, that is the ultimate challenge of fluid engineering.
It is an incredible journey when you step back and really look at the whole picture. I mean, we started today by looking at the invisible polar attractions between two microscopic water molecules, and we followed that exact same thread of logic all the way up to calculating the precise pressure drops across miles of massive industrial pipelines.
It really shows how understanding the smallest underlying mechanisms gives you the power to manipulate the macro world.
It totally does. Well, we're going to leave you with one final thought to mull over. Next time you are out in the yard and you turn on a garden hose, and you instinctively put your thumb over the end of the hose to make the water spray faster, Think about what you are actually doing in that exact moment.
You're doing quite a lot of physics.
You really are. By making the opening smaller, you are forcing the continuity equation into action, physically accelerating the mass flow rate. Because the water is speeding up, you are forcing the pressure energy to drop to balance the scales. And because of that sudden velocity jump, you are drastically shifting the Reynolds number, triggering chaotic, turbulent flow. When you put your thumb over a hose, you aren't just watering the lawn, you are holding Bernoulli's principle right in the palm of your hand. Thank you so much for joining us on this deep dive. We will see you next time.